Hello, I'm Sukyung. The paper I'll review today is Neighborhood Overlap-Aware Heterogeneous Hypergraph Neural Network for Link Prediction. This study was published in 2023 and it introduced graph structural information learned from overlapped neighbors to maintain graph topology, thus assisting to link prediction. Graphs have gained significant attention in recent years. Real-world systems typically involve multiple types of entities and interactions. Therefore, heterogeneous graphs and heterogeneous information networks serve as more general modeling tools. This paper focuses on the link prediction task on heterogeneous graphs. Heuristic methods estimate link existence by computing similarity scores based on predefined graph structural features. However, these approaches are primarily designed for homogeneous graphs and cannot be directly applied to heterogeneous graphs. On the other hand, heterogeneous graph embedding methods aim to transform HGs into low-dimensional vector representations. Early studies mainly adopt proximity-preserving strategies such as random walks. More recently, neural network-based approaches have been introduced for HG representation learning. Despite their success, these models still exhibit several limitations. First, most HGNN-based methods focus on pairwise interaction and fail to capture higher-order complex relationships among multiple nodes. Second, existing approaches place excessive emphasis on node attributes while underutilizing graph structural information. To address these limitations, this paper proposes a novel HGNN framework that incorporates heterogeneous graph structural information while modeling higher-order relationships between nodes. Heterogeneous graph embedding aims to project nodes from a heterogeneous graph into a low-dimensional vector space. Early HG embedding methods typically initialize node representations randomly and optimize them using well-designed objective functions. Decomposition-based methods divide the heterogeneous graph into multiple subgraphs. However, these methods often lose important information from heterogeneous neighbors. Random walk-based methods address this limitation by using metapath-based random walks to capture both structural and semantic information. The development of message passing algorithms, graph neural network-based methods have been widely adopted. Encoder-decoder-based methods encode node attributes and preserve graph properties through a decoder. However, existing methods still fail to effectively utilize graph structural information, which leads to suboptimal performance in link prediction tasks. Link prediction aims to infer the existence of relationships between node pairs in a graph, and it has attracted significant attention with various methods being proposed. Most approaches fundamentally compute similarity scores between node pairs based on graph structural information and determine whether a link exists. In homogeneous graphs, traditional methods mainly rely on structural features such as common neighbors and shortest paths. To avoid manual feature engineering of structural information, embedding-based methods have been introduced. With the development of graph neural networks, various GNN-based models have been applied to link prediction. In heterogeneous graphs, link prediction is mainly based on heterogeneous representation learning, and GNN-based approaches have become the mainstream. However, these existing methods still fail to effectively utilize graph structural information. These notations are defined to help understand the equations proposed in this study. Consider a heterogeneous graph GH with multiple types of nodes or edges, where VH is the set of nodes and EH is the set of edges. Similar to a heterogeneous graph, heterogeneous hypergraph G is defined as a hypergraph containing several types of nodes or hyperedges, where V denotes the set of nodes, where E is the set of hyperedges. For a more detailed explanation, please refer to Table 1. To better represent semantics, nodes in the hypergraph are categorized into two types. First is identifier node. It determines the semantic meaning of a hyperedge. Each identifier node belongs to only one hyperedge, and the type of an identifier node is determined by the event it represents. Second is slave node. It is a member node that participates in a hyperedge. It works together with the identifier node to describe complete semantics, and a slave node can be shared across multiple hyperedges. This is the overall research framework named KNOW. KNOW consists of a heterogeneous hypergraph variational autoencoder that learns the embedding of a heterogeneous hypergraph, as well as a neighborhood overlap-aware method that generates node representations only based on structural information. To run node embeddings and higher-order relation embeddings, it designs a heterogeneous hypergraph node encoder and a heterogeneous hyperedge encoder. Heterogeneous hypergraph decoder is designed to get the original hypergraph topology. First is the heterogeneous hypergraph node encoder. To map the HG from observation space into a latent space, it designs a heterogeneous node encoder as follows. Then, model obtains the means and variances by two linear modules, and z to the power of vk is gotten by following step. Next is the heterogeneous hyperedge encoder. To capture the higher order semantics and complicated relations provided by hyperedges, it designs a heterogeneous hyperedge encoder. First, it learns the potential representation of the hyperedge. To learn the importance of various types of nodes in each hyperedge, it designs a hyperedge attention module. First, it transforms the type-specific embedding into a common space and calculate the importance weight. Next, normalize via softmax and compute hyperedge embedding, then obtain mean and variance. Last is heterogeneous hypergraph decoder. It designs a heterogeneous hypergraph decoder to reconstruct the hypergraph. The decoder generates random variables from the node embedding and hyperedge embedding so that the original hypergraph topology can be reconstructed. To learn node representations in HG with structural information, it proposes neighborhood overlap-aware GNN. The neighborhood overlap-aware GNN consists of a neighborhood overlap-aware aggregation schema and a graph structural information generator. First, it extends the agency matrix to multi-hop neighbors. Then, it designs a graph structural information generator F-zeta to run to generate node representations from the L-hop matrix of the graph. Based on upper expression, it obtains the node representations of the HG and uses the binary cross-entropy loss function to train. It splits the node representation ZST into the identifier node embedding and the slave node embedding by a split step. Then it fuses the generated node representations with heterogeneous hypergraph embedding. And last, the loss function in proposed node is expressed as follows. Given a link ij consisting of a slave node I and an identifier node j, it calculates the similarity between the two embeddings using the embeddings z to the power of hyper and z to the power of node to the power of k. The statistics of the datasets used are shown in Table 2. 4 types of datasets were used in the experiments, and detailed information about the datasets is described on pages 20 to 21. It compares proposed node with two kinds of graph representation learning models, which are homogeneous graphs and heterogeneous graphs. Tables 3 to 6 show the results of the baselines and node on the 4 datasets, and the results of the studies demonstrate that state-of-the-art performance is constantly attained by proposed node across all datasets. It presents evaluation experiments to observe the effectiveness of the different components of node. As shown in Figure 3, node shows state-of-the-art performance compared to those without one. Here is the conclusion. This paper proposes nodes that learn higher order semantics while maintaining original graph topology, which improves the performance of link prediction. It adaptively combines the heterogeneous hypergraph variational autoencoder and the neighborhood overlap-aware GNN to consider both heterogeneity and graph structural information. One area for improvement is to enhance the design of more complex aggregation functions during the process of learning graph structural information. In future work, it intends to further improve the efficiency of model and effectively apply it in industrial pattern recognition. Thank you for listening.